UNM now, well, we're doing hybrid this semester, so it's sort of confusing because I've got a class where I've got a couple remote students, but I've also got several in-person students, and it's teaching to two different audiences. I don't know, Derek, if Carrie's class, I think, is 100% on in person, but
yep, we're fully there.
So let me introduce my co-conspirators. There's Carrie Howe, who is professor, and he's director of the Center for Water Resources. Odell Lee is a postdoc. Caitlin Fisher is director of laboratory services or something like that in the civil engineering department. And so I'm focused on brackish water, and the title doesn't reflect that, but we are focused on brackish water, which is, at least for our purposes, a TDS of less than 10,000, something like that. You know, we had hoped that we could apply it to higher salinities, but there's a fundamental technical limitation, and I'll get into that. Nevertheless, this is a map that was done back in, well, the earliest I found is 2004, but I think it predates that. This is a map of brackish water resources in the state of New Mexico, way back in 1962. Steve Reynolds, who was a state engineer, claimed that 75% of groundwater in New Mexico is either brackish or saline, and it was based on maps like this. And the problem is that last bullet there. You have to recognize that a two-dimensional map gives very incomplete picture, because there's these aquifers, many of them are very deep, and of course, as you go deeper and deeper, the productivity of the aquifer, its yield decreases. And so there was a study that I'm not going to talk about. I've given talks about this as well, but there was a study done about 10 years ago for the Water Utility Authority, and you know, they were comparing, they were examining the possibilities of deep brackish water, principally to the west of western part of Bernalillo County and some over in the east, and they found there was not nearly as much water as they had hoped, and it would be very expensive to produce it, never mind to treat it. So, but nevertheless, there are brackish water resources that are being tapped in New Mexico and beyond. Perhaps the most famous is, and best known, is the brackish water desal plant in El Paso, the K. Bailey Hutchinson plant, which treats water with an influent TDS of about 3,000, maybe 3,200 milligrams per liter. So it's too salty to drink, but it's a very large resource. So there are a number of challenges. The first of all is the challenge of scale formation. And brackish water, the chemistry of inland brackish waters is much different than for seawater. Seawater is 95 to 98% sodium chloride, which has very little scaling potential, whereas brackish groundwater, it's got hardness ions, calcium, magnesium, it's got sulfate, it's got very high, often has fairly high alkalinity. And so that limits your ability to recover a high fraction of the water without encountering scale potential. Another one is the challenges of concentrate disposal, the brine disposal. And there was a guy that worked for a consulting company, Herkenhoff, his name was Charlie Leader, did a study. And I don't know, Charlie, I've got that on my desk over here. I should have pulled it out. But Charlie did a design study for brackish water desal project in western Sandoval County, west of Rio Rancho. And they found that the concentrate disposal was going to be about 50% of the cost of the total plant. Deep wells are going to have to pipe it a long ways, whereas a coastal desal plant can just, dump the water back into the ocean. In El Paso, they pipe the water 22 miles to disposal wells. So that's an expensive pipeline. But it's so concentrate disposal is a very, very difficult challenge. Some places, for example, Sandoval County, that water was going to, by the time they had concentrated it by the RO process, it was likely going to have the characteristics of a hazardous waste. It's going to have high arsenic, high vanadium. There were a couple of other constituents. It was also going to be radiologically hot. So not only might it be classified as a hazardous waste, but it might be classified as a radioactive waste. So concentrate management is a big, big issue in inland desal. So I'm talking about the 5 major challenges. One is the technology. Again, the nature of the constituents that are in the water pose a big challenge for recovering high fractions of the feed water. The cost and energy requirements are very large. The magnitude of the brackish water resource, as I said earlier, these are low yield aquifers. They're typically they're deep. They have low hydraulic conductivity and very low storage coefficients. Concentrate disposal, and then sustainability. And this is an issue that I'm not talking about today, but the idea is that in Western Sandoval County, they were talking about brackish water resource, and the developers claimed that there was a 50-year water supply. I went back and looked, and I found some fundamental problems with their assumptions, and I think there's more like a 20-year water supply. And so the question becomes, after that water supply is gone, what's the community going to use? Will a banker give a mortgage loan to a 30-year mortgage loan to a homeowner when he knows that the supply may only last 15 or 20 years? So we developed here at UNM, principally Carrie and I, the MRED process, mineral recovery enhanced desalination. And it is focused on bullet items number 1 and number 4. So it's to improve the desal technology and to facilitate better options for concentrate disposal. So the process was developed to pre-treat. So it's not a desal process per se. It is a pre-treatment process which removes the scale-forming minerals. We talked about calcium, magnesium, sulfate, carbonate. Often we'll have high silica. I think out in Western Sandoval County, the silica concentrations were pushing 100 milligrams per liter, which was going to be a big, big, big problem. It will recover commodity minerals, principally magnesium hydroxide and gypsum. And so instead of having a waste product, we've got something that we can, in principle, sell. Now, in practice, these are low value minerals. There's very, very little
Is that muted, Bruce Freeze?
I think we're having some streaming issues.
I think Bruce froze. They probably don't have a very big internet connection at UNM, so he may have to log back out and log back in. Let me see if I can chat him.
Sounds like we can disband this whole organization since there's not enough water out there that we think we could have tapped. What do you think, Mike?
Bob,
We thought we had Bruce over on the pro desal side. Now he went back. He's
Morton Salt Company is really excited about this.
It just speaks to the need for collecting good water data.
there you go, Jerry.
You got to have the data first, then you can decide.
Well, and by the time we get all the data, we'll be out of the fresh water. So it'll be a good time. We'll have the data, we'll have no fresh water, and then we'll have to go through the permitting process.
There you go. Who knows how long it'll take to get a state engineer either.
You know what? There you go. This could be an omen because Bruce may be wrong. They may be really deep aquifers.
Okay.
Okay, I know you're
Coming
getting
back
the deal.
on.
Hey, Bruce, we just found the depth of the major aquifers in New Mexico, and they're miles, like 30 miles deep. We got 50,000 years of water down there.
Yeah.
It's all TDS of 80,000 though.
Okay, am I back?
Yes.
You're
you are.
back in business.
I do not know what happened. I'm calling from my office and I've never frozen before.
Huh.
Okay, so we developed, I'm gonna jump back in. The two principal benefits of this is to remove the scale forming minerals and to reduce the mass and volume of waste requiring disposal. Okay, so we developed this with a grant from the Department of Energy, and here is the technology, and I'm not going to go through it on this slide so much, but I will go through it stepwise. So the first step is to remove dissolved CO2. So we're removing carbonate ions. So once we do this, we don't have to worry about calcium carbonate, limestone precipitation, or other carbonate minerals. Okay, the next thing we're going to do is we'll precipitate magnesium hydroxide just by raising the pH. Then we go over, we remove calcium with cation exchange. After the magnesium hydroxide, the only divalent constituent is calcium. So we remove that by cation exchange. Now we've removed all the divalent ions, the calcium, the magnesium, we've removed iron, we've removed silica. So the fourth step is nanofiltration using a membrane softening, sometimes it's called, and we'll remove the sulfate. And then now we've got a very soft water. It's strictly dominated by sodium and chloride, so we can do very high recovery with our reverse osmosis or thermal desal process. So I'm going to go through this in a sequence. I'm going to use cation and anion balance, and that's that bar chart up in the upper right-hand corner. So most of this discussion is focused on this water from flue gas desulfurization process, but I've done the same thing for the waters at Biggendorf at well 1 and well 2, and I've done it for well 3. But let's look at this bar graph up there. The cations, the positive ions, are the top bar. So red is sodium, gray is calcium, and what is that? Purple, I guess, is magnesium. And there's minor other elements. There could be iron, there could be potassium, but those are usually present in much smaller concentrations. The anions, the green is alkalinity. That's our dissolved CO2. That's this stuff down here, 150 milligrams per liter of alkalinity. Yellow is chloride, and what's that other? Magenta is the sulfate. So those are the major ion constituents, and we're going to go through this in sequence and see how we remove them. So I'm not going to deal with this. This just says that calcium carbonate, the green line, that's our limestone. That's the precipitation. As the pH goes up above about 7 or 7.5, we have to worry about lime precipitation. But everything, yeah, so there we'll just leave it there. So the first thing I'm going to do is at low pH, we'll do the air stripping. That's step number 1. We're going to acidify it to pH 4.5, which is not all that low, and then air strip it. Then we're going to raise the pH to 10.5 and remove the magnesium. And so we've done that. And this is the water coming in. So we remove the magnesium. And this shows the solubility. This is based on lab experiments. It shows that once you get above pH 11.5, this percent removal, we remove virtually all of the magnesium hydroxide. It's very high purity, 95%. It'll also remove silica. It'll remove arsenic. It'll remove iron. High pH precipitation removes a lot of problematic constituents. And this is what it looks like. The problem with this darn magnesium hydroxide is the darn stuff does not settle. And you can see, you know, we at 0 minutes, it's very turbid. At 55 minutes, it still hasn't even settled half of the column length. And the reason is because these are very fine particulates. So what we did next, well, if you can't settle it, we'll filter it with a membrane filter. We ran membrane filtration tests, pH 11, and it does a great job. And the advantage of magnesium hydroxide, if it does foul the membranes, all we got to do is run a dilute solution of citric acid or some other acid through there, and it cleans the membrane almost instantly. It's very, very soluble once you get below about pH 10. So the magnesium hydroxide was removed by high pH precipitation. Then the suspension was removed by membrane filtration. And again, we got very high fluxes in excess of 200 LMHs, liters per square meter per hour, which is a very, very high flux when you talk about filtration experiments. So the next process was the cation exchange. Remember, the water leaving the magnesium hydroxide, we removed all the divalent ions. We removed iron, we removed manganese, we removed magnesium, certainly. So the only divalent ions left in this divalent cations are calcium. So coming into my cation exchange, we've got high concentration of sodium and calcium, but we removed all of the magnesium. There's no magnesium in this solution. We run the experiments, and the problem, and this is the limiting factor in the whole process, and that is that as I'm going to go back to my rules for ion exchange, the polyvalent ions are preferred over monovalent ions. So calcium is preferred over sodium, aluminum is preferred over calcium, and so forth. High atomic number ions are preferred over low atomic number. So calcium is preferred over magnesium and so forth. The problem is this number 3, at high ionic strength, at high TDS, these selectivity rules reverse. And that's, I'm not going to go into this selectivity charts, but it shows that when we get above an ionic strength of about 0.1 moles per liter, 0.15 moles per liter, the selectivity rules change. So we ran these things with our low TDS water, that water that I've been talking about with a TDS of 4,500 milligrams per liter. We can remove about 80 bed volumes before we get breakthrough. Now, if I was going to run my home water softener where the ionic strength is about 0.02 or 0.01, I can probably get 200, 300 bed volumes. So that's an example of the diminished performance. And if we go up to an ionic strength of about, a TDS of around 15,000 milligrams per liter, it doesn't work at all. So the maximum TDS is determined by our ionic strength. So after we do the ionic strength, we removed all the sodium, we removed all the calcium. I'm sorry, I misspoke. We've removed the calcium, we've removed the magnesium, we've removed all the trace constituents as well. So now we're going to regenerate it. And the way we're going to regenerate it is we're going to take the salt, the concentrate from our desal process. We're going to run it back through the cation exchange unit. So we don't have to regenerate by going out and buying salt like you might do if you had a home ion exchange unit. We've got a ready-made source of salt right here from our desal process. Okay, so we desalinate it. We run that brine back into a big old tank right here. We're working with a 100-gallon cone bottom polyethylene tank in the lab. So when we regenerate it, this regenerant right here has this water chemistry. It's got high ionic strength. You can see its ion concentrations, 1,200 milliequivalents per liter. It's dominated by calcium with lesser amounts of sodium. So we flush the calcium through with our regeneration process. Okay? As the TDS goes up, the performance of the ion exchange goes down, which is, as I've said already once, this is the factor that limits the maximum TDS of our process. Now, if there was some magical way we could come up with a better ion exchange resin that would work at higher ionic strength, we could treat higher TDS water, but right now that's the best we can do. And there are chemical reasons. It's not just that the manufacturers can't make a better resin. There are some fundamental chemical reasons why we're limited there. Okay, so we've regenerated the cation exchange resin. The water that's going into our membrane softener, our nanofiltration unit, now only has sodium and chloride and sulfate. We remove the carbonate up here with the degasification. We removed our magnesium, high pH precipitation. We removed the calcium in our cation exchange. So the only cations coming in here is sodium. The only anions coming in are chloride and sulfate. And so that's what the water looks like. Here's my bar chart up there. Sodium is the only cation present in high concentrations. The anions are a combination of chloride, which is the yellow, and the sulfate, which is the magenta. So we run that through our NF unit, and we're getting moderate pressures. These are not super high pressure, 77 to 150 PSI. We get, somewhere around 9% rejection of the chloride. We get 96% rejection of the sulfate. Okay, because these membranes are, they preferentially allow monovalent ions, chloride, to pass through them, but they retain divalent ions. And then in order to keep an ion balance, we've got to have some sodium in there. So some of the sodium leaks through as well. After the NF, we've removed all of the divalent ions, the calcium, the magnesium, the sulfate. The concentrate is this. This is the brine that comes off the NF. So it's got sodium in it. It's got chloride, and the magenta, again, is the sulfate. So I go back over here. Here is my NF. The concentrate is coming off the, that's what is retained by the membrane. And we mix that with our calcium from the ion exchange. So we've mixed the calcium with the sulfate, and we get gypsum precipitation. And that's this next process right here. The calcium from the IX regenerant, the sulfate from the NF concentrate, and this gypsum, pH independent. That's the red line right there. And the gypsum precipitates like a rock. So you can see in 0 minutes, we had a turbid solution. In 5 minutes, we have 90% of the solution is clear, of the settling column is clear. And the reason is this stuff is beautiful, beautiful crystals. And they're pretty good sized crystals. It's a crystal, the name of the crystal is, or the mineral form is selenite, and real pretty, settles like a rock. And so we don't need to go to any type of fancy removal process. We don't have to go back to membrane filtration. The supernatant, this is the water up here, has high concentration of sodium, high concentration of chloride, still got a pretty high concentration of sulfate and calcium. And because gypsum is pretty soluble, so we're going to take that supernatant, the stuff that did not precipitate, we'll run it back through the process so we don't to reduce the volume of solution that we have to waste. So the last step is a desal process, and we modeled that as RO, but it could also be a thermal process, flash distillation, conventional distillation, membrane vacuum extraction, whatever. It doesn't really matter. The point is right here at point number 5, our water is very soft, very soft. It's dominated by sodium and chloride. So it's, in many respects, it's analogous to seawater. So instead of recovering 50% or 60%, 75% like they hope to, well, in El Paso, they claim 75% recovery, but it's, there's some challenges there. We can recover 90-95% of this water here. So here's the water coming in. It's a sodium chloride water. The water coming out, this is the permeate. This is the desalinated water. It's very soft and has low TDS. And then the concentrate is a sodium chloride water. And that's the water that we use to go back and regenerate a cation exchange. So we've been talking, that's also this water here, the concentrate that goes to waste stream. It's mostly a sodium chloride. And there is a firm that we've been talking to is quite interested in this brine because they can use it for industrial chemical processes, including on-site hypochlorite generation for water desalination, water disinfection, I'm sorry. So this is we're not trying to sell the brine, the concentrate as a product, but it might have some commercial value in some locations. So let's just summarize. The water that comes in is a mix. Again, the cations are sodium, which is the red, the calcium, which is the gray, and the magnesium, which is the magenta. The anions are alkalinity, chloride, and sulfate. As we go through our first step, the first thing we do is we remove all the alkalinity, that's the green down here, and we remove all the magnesium, that's our high precipitation, high pH precipitation. Then we go to ion exchange, that's right here. After the ion exchange, we've removed all the divalent cations. We've removed calcium, we've removed magnesium. So the only cations left in solution is our sodium. The anions, includes the full spectrum, the chloride and the sulfate. Then we run into the nanofiltration softening. So the water coming out here is a very soft water. And finally, after reverse osmosis, we've got water with very, very high purity. So I constructed a model, a balance. Here is the summary of the flows. It's a mass balance for treating that 4,500 milligram per liter TDS. Coming in, I've got 1,900 cubic meters per day, which is 500,000 gallons per day. It goes through, I add a little bit of acid. I have to add acid to lower the pH. I have to add a little bit of base to raise the pH. The magnesium hydroxide, we're removing 143 cubic meters per day of a slurry, a magnesium hydroxide slurry. We add a little more base, comes down here. Go through the cation exchange. We're recovering 58 cubic meters per day as our 58 cubic meters per day as our regenerant. 1,800 cubic meters going to NF, 1,500 meters go from there. And the final recovery is from 1,900, we're recovering 1,560. So instead of doing 50% recovery, I think the pilot testing out there in Sandoval County, they actually did, what was this, the scale, 30 gallons per minute or something like that. Very large pilot test. They were doing about 25 or 30% recovery of the feed water. Here we're doing 75, 80%. And if you factor in some of the recycled things here, here's our influent, here's Biggendorf well 2, we're doing 85% recovery. The mass of magnesium hydroxide is 1,400 kilograms per day dry weight. The volume is something on the order of 223 milligrams per liter, mass of gypsum and so forth. But again, the big deal is we have recovered 85% of the water instead of 50 or 60 or 70%. So the limitation of the work that we've done to date, these were batch experiments. You saw the scale. Some of them were very small scale. Most of them were done with volumes of a couple of liters or less. The testing was limited to simulated fluid gas desulfurization water. We have not tested Biggendorf water. We did do some work. I didn't mention it here. We did do some work with removing hazardous constituents, arsenic, selenium, and mercury, and which is, it's not a surprise that the high pH precipitation removes those constituents, and what is not removed by the high pH precipitation is removed by RO. So what we've got now is we've got money from the Bureau of Reclamation, and we are building a 1 gallon a minute pilot unit. And man, it's amazing. The complexity is quite intimidating. And these are the questions we're trying to address with our pilot unit. Can we improve the magnesium hydroxide precipitation by doing some nucleation experiments and things like that? Can we extend ion exchange to higher ionic strengths? Can we improve the gypsum precipitation? As I said, the residual calcium and sulfate concentration is a little bit of a problematic. And then we want to improve and expand our process flow model. We're going to test 4 waters, UNM tap water, and then the 3 waters at Biggendorf. We're doing volumetric and mass flows. We're calibrating the model that I developed. We're testing the operating parameters, flow, pressure, and temperature. We want to look at the composition of those commodity materials to make sure that they are not, they are sufficient purity that they have some value. So, worst case scenario would be our magnesium hydroxide's got 50% contamination by calcium or something like that. And that would diminish its value for a potential subsequent reuse. And then cost use. So this is the piping and instrumentation diagram. It's, pretty much the same diagram we saw. We've got pressure, a pump coming in. We've got air stripping, acid and base addition. Here is our membrane filtration process, ion exchange, nanofiltration, reverse osmosis. We're doing our gypsum removal in a polyethylene cone bottom tank. We're recycling the water. And so that's where we stand anticipated outcomes pretty straightforward. We think we've got something that has considerable application for inland desal processes. And the perfect one would be El Paso. If many of you are familiar, there was energy water minerals company that tried to build actually built a plant adjacent to the K. Billy Hutchinson plant to recover some of these things. It was a much more complicated process than ours. We think this has application there. If Charlie and the Water Utility Authority want to go into the Brackish water development, water resource development process, we think we have some ideas here that can improve the recovery and reduce the concentrate disposal costs. So we've been talking, Grizz has been helping us quite a bit. We've been talking to a couple of private partners. One of the biggies shall remain nameless for now, but they're very interested. They're somewhat skeptical, and they want to see the results of our pilot test. So I think that is where the proof is going to be, is once we can operate one of these things for a few months, then I think we'll have something that has some real significant market value. So with that, I will turn off my share screen and thank you very much and take questions.
Well, we've had some roll in through the chat, and I'm going to try to paraphrase them. As a note in passing, when this process generates magnesium hydroxide in sufficient quantities, give Mark Holstead a call, because that's something he's using for odor control in the collection system, and he's having to pay commercial companies for that product now. So I'm sure he's quite interested. And as far as the concentrated sodium chloride brine, we, the Water Authority, could be very interested in that, you know, once it's the solution commercially available, because right now we're paying, we found one maker of solar salt in and around the Salt Lake City area, and they're trucking in salt and distributing it all throughout our water treatment facilities, our groundwater wells, as well as our surface water plant. If there was a way around that, instead of having to make this up from salt, that could be very interesting. And I'm sure there are other utilities that are looking to do on-site hypochlorite generation. And if this were a feedstock they could use for the process, that could be quite interesting to them. Let's see if I can go through the questions in the chat. Let's see, one of them that came up, it points to, let's see, it says Eric Dole probably has more insight here, but have you considered cost benefit of implementing electrocoagulation versus proposed degasification and mag hydroxide precipitating on membrane filtration? Eric, did you happen to hear that one? Are you still with us? Well, he's muted if he is.
Well,
But
let
anyway.
me, we're not doing any coagulation and filtration. So I don't think that would have an application. We need a little bit of mineral acid to lower the pH to strip out the dissolved CO2. Once we've removed the CO2, the solution has very, very little alkalinity. And so therefore we can adjust the pH with very small volumes of acids and bases from there. So I don't see an obvious application of electrocoagulation, but that is something that we will look at. So I appreciate that suggestion. Let me write it down.
By the way, for those that are familiar with the Water Authority's enhanced coagulation process, we drop the pH and we turn around and readjust the pH to get it back up. I refer to this as the X-lax ammonium process. And what you've got going on here is certainly a different variation of the same thing. Drop it to pH 4 and then raise it back up to pH 10. Must be fun to watch in the test tubes, that's for sure.
You know, the interesting thing is, like I said, we've destroyed the alkalinity in the very first step. And so after that, it takes very, very little amounts of sodium hydroxide to raise the pH. And then after we've done the high pH precipitation, takes almost no acid to bring it back to neutral. And in fact, because we remove the alkalinity, we have a problem bringing the pH back to 7 because there's no more alkalinity. You know, we'll overshoot and undershoot. So it's not a problem for what we're doing, but it is sort of an interesting phenomenon. When you start playing with alkalinity, life gets interesting.
Okay. Zach had a couple of questions here. It was, Bruce, what is your water source? I think that was defined. And what is your total recovery? I think he dropped off before you showed that slide. Now here's the curveball. How do recoveries compare to an emerging RO technology like CCRO, whatever that is, enlighten us, or flow reversal RO?
Yeah, so, you know, those are also subject to the same limitations that other desal processes, mainly those scale minerals. And so the recovery, we could use any desal process at the tail end. We're not selling desalination, we're selling pretreatment. We're proselytizing, not selling, because we don't have anything to sell yet. So the big, with respect to those high recovery technologies like CCRO or flow reversal RO, the big advantage, if they can get the 80 or 90% recovery from these hard brackish water sources, more power to them. They've still got a very difficult waste management problem. And by doing our technology, we've cut the waste management problem in half. We've cut the waste management problem. And like I said, Charlie, based on your work, which I refer to that all the time, and
I had no
I'm
idea.
very impressed with that study, Charlie. But I refer to that all the time. If we can reduce the volume and the mass of the concentrate by 50%, there's a very substantial cost saving.
Most of those, like the CCRO guys, when you start reading the fine print, you know, they pretty much want ocean water. So they're going to have, especially since they're closed circuit, the buildup of scale is actually kind of a bigger problem for them. You would think they would need something like this to really be efficient outside of just plain seawater.
Thank you.
Diaco, I'm sorry if I mispronounced your name. You had a question,
Yeah,
Dr. Thompson, on slide 16. Go ahead. Rather than my paraphrase it, let her rip.
thank you. Well, my name is Diaco. I'm a PhD student in chemical engineering. I have a question on slide 16. Yeah.
Which school, homie?
OSU, Oklahoma State University.
Oh, well, thank you for joining us. Great.
Thank you. Well, so you explained that the flux is really high, yeah, but you know, as you know, one of the most problem with membranes is like drastic problem is fouling. We need in order to get like have a like decent evaluation of the fouling, we need to test the membrane for a long time, like at least 48 hours or 2 days, because once we start the membranes, we have like initial flux and then the flux decrease. As you can see, after 80 minutes, like for run 3, we don't see any stable flux. So to have like a correct evaluation of the flux, we need to run the membrane at least for 24 hours to get the stable flux. That's why. And another thing is, in order to evaluate, like calculate the fouling, we need to like calculate FRR, flux recovery ratio, to have like a big picture about the fouling of the membrane. So my question is, do you have any plan to like run the experiment for like 24 hours or?
No. So let me answer the last question first. We don't want to run it for 24 hours. We want to run it for 6 weeks. Okay, so that's the whole purpose of the pilot test, was to run this thing for an extended period of time to test exactly those points you brought up. To run this as we did it in the lab, we were making up 50 gallons of water and testing it and making up another 50 gallons. I mean, it's a pain in the patooth. The other thing regarding fouling, for inland waters, the principal fouling minerals are limestone, calcium carbonate, calcite, aragonite, whatever you want to expect it. And by removing all the dissolved CO2, we eliminated the potential for calcium carbonate fouling. And the other one, out here in New Mexico, a lot of our waters have very high silica, particularly the deep ones. The solubility for silica is somewhere around 120 milligrams per liter. It depends on a bunch of parameters, but 100, 120. Many of the typical wells, the well that Charlie was working on out there in Sandoval County, their silica, they were already at the saturation level for silica. Well, we're going to remove the silica by the high pH precipitation.
Mm-hmm.
Hopefully, we expect that the silica will not be a fouling problem. It will be in precipitate form. It will not be in solution. So that's the issue. And then last thing, we did do some electron microscopy of these membranes, and after we cleaned them, there was nothing on it. So those are very good points, especially the long-term testing.
Okay.
We absolutely recognize and agree that that's important.
Okay, so you clean them with DA water, deionized water will just like wash them.
Yes.
How did you regenerate the membrane? Sorry.
Tap water backwash.
Okay, clean with backwash. Okay.
Diaco came on later. He is being sponsored by the National Science Foundation to spend 6 months with us at Nine Water so we can ruin him. He's a PhD candidate, a scientist in a company full of engineers. So he's working on new membranes.
Are you working with Jorge?
Excuse me?
Have you met Jorge? He's a new assistant professor. Jorge Gonzalez, I think. New professor at OSU. It's okay.
Actually, it's Ohio. You know, he's working Ohio State University.
Ohio. I'm sorry.
Oh, we thought we had an. We thought we had an Aggie here.
OSU, Oregon, Oklahoma, Ohio. Yeah.
All right.
Come on, Mike. Ask me some penetrating, insightful questions.
So the question I have is, when are you going to do it at Bergendorf? This summer, or when's your plan?
You know, we're running up against two problems. One is we have not been able to find a graduate student to work on this. When we mentioned spending the summer at Bergendorf, they run away screaming.
Get a tan, maybe learn a second language. I mean,
Yeah,
you know.
really. So we've been limited. We've not found a grad student. The second thing is we've run into supply chain issues. So we need to buy, for example, membrane filtration unit cartridge from Coke Separation Systems, and they've got one. We need two. We bought some data acquisition systems. We needed, I've forgotten, we needed 5 flow meters and they had 3. They had 3. pH meters, we needed 6 pH probes, we could buy 4. And so we're running up against that kind of stuff again. I think all that stuff is sitting in freighters in Los Angeles Harbor. But we're building the system now. I work on that 2 or 3 mornings a week, and it's starting to come together. But we want to test at least 3 waters at Bergendorf. 2 weeks
Okay.
each.
Hey, Bruce, this is Jerry. I'm wondering what do you think would be the impact of in your influent water of any kind of organics on your system? Is that a total category killer?
Nope. Organics are going to be removed by the high pH precipitation. Some fraction of them will. Some organics, the cationic organics, may be removed by calcium, but the rest of them are going to be removed by our nanofiltration process. You know, nanofiltration is a great process for removing organics. So we've got, and then finally, nothing's going to make it through our own. So, but the main thing is the nanofiltration. And if we have to put activated carbon in there somewhere, that's not a big deal.
There are other media.
Go for it, John.
We do know about that.
Hi, Bruce. This is Eric Dole. I got a quick question for you. Have you taken a stab to try to do any analysis if some of this water has PFAS in it, and if it makes it up in your high purity brine stream, which I imagine it would?
Yeah, you know, that is an issue, because if you concentrate it, you know, by a factor of 10, which is, you know, what you would get if you had 90% recovery, PFAS could be a problem. The process, since it's an RO process or some type of a desal process, my guess is you'd have pretty good removal of PFAS, but the concentrate would be problematic.
Pretty nasty. Yeah.
But at the same time, now you've got a small volume, high concentration. It will be much more cost effective to treat the PFAS in the concentrate than try to treat the PFAS in the permeate or the feed water.
I'm having some pretty good success with destruction of PFAS with electrocoagulation. So if you want to talk with me later about maybe possibly teaming up with you on some of this, that'd be great.
Yeah, sure. And who are you with, Eric?
I'm with Garver Consulting.
Oh, okay. Oh, yeah. Okay.
It's a great concept, though. Thank you for presenting.
Any last questions for Bruce? This was really quite.
Yeah, I do have a question. Bruce, is there any way we can help you? In other words, you need a graduate student. I don't know that we can find one, but sometimes we have students that last year we had some students that from New Mexico State that were there at Alamogordo all the time, running systems for people. So I don't know, we may be able to work something out with you. Maybe a New Mexico Tech student, I don't know, but is that okay? I know that's not the optimum, I'm sure, but is there a way we can try to help you through?
That's a great suggestion, Mike. And as we go forward, now Carrie is teaching a class this semester of last semester seniors and graduate students. It combines undergrad, graduate class. And Derek said he's taken that. And Carrie was going to see if he could recruit a student from there. We've got some other options. But yeah, that's a great suggestion, and we may take you up on that.
Okay.
I can remind him today. I'll see him in about an hour for that course.
Yes. Yeah, remind him. Thank you. He hasn't mentioned it in class yet?
No, not yet.
Remind him.
Okay.
So this past summer, there were some students from New Mexico, Michigan Tech, up in the UP that were there as a fellows for the BOR that were working at Bergendorf, and they worked on a couple of projects. And maybe we can talk to Melinda and work something out for you that way. And maybe we can share something. We can have somebody that could do some work with us while they're doing work for you.
That's a great idea. And kind of the worst case is they might find some old geezer professor who might want to go down there for a few days at a time.
Yeah. Okay. You don't got any geezers in mind? I know a lot at UNM. I know one in the civil engineering department I might talk to. Yeah.
Good suggestion. I appreciate that. Hey, well, thank you very much for inviting me. Again, I think it's a great organization. I participate as I can. And if you would change the date of your meetings from the fourth Thursday to the third Thursday, I would be a more reliable participant.
Yeah, we're gonna keep it the same.
Yeah.
Changing.
Matter of fact, find a day that you can't join, and that's what Bob is going to suggest we change it to.
Mister, we're running out of brackish water. So what the hell are you even working on this stuff for?
Well, there are applications. There are places.
That's a board professor.
Brackish water doesn't always have to be groundwater.
Correct. It doesn't have to
True.
be groundwater. The water that crosses Pecos River water that crosses into Texas would be perfect for this. It's typically got a TDS of 1,500 to 3,000, so that would be one. The other thing is there are industrial applications, and again, Grizz has helped us try to find some industrial collaborators, and it's a niche. It's a niche process.